Testing. Thank you for your patience. So now I'm ready for like the delivering the lecture. Yeah. Then I have released the left two grades, and then like for the late submitters, so your grades are not counted yet. But whenever your submissions are available to the GitLab, then my grading script will automatically fetching that and then put the grade on it. And then I will run the grading script on every weekend. So please let me know if your score has not updated for a week. Yeah. And then today we will learn about the details about the system calls and the page fault, and then how we can handle that correctly. So let's do a little bit of recap about what we have learned for the last week. And we learned about how user execution can switch to the kernel, and then kernel execution can launch the user program back and forth. And then that's how the modern operating systems are managing like running multiple processes at the same time. So it looks like it runs at the same time, but what it actually does is like it stops on 1 millisecond and schedule the another one. And before getting to that, we have learned about how the user level process ask operating system to access the hardware. And one of the examples is that just running printf to print some of the characters on the console. And to do that, a user level program can invoke a printf function call. But even if you didn't write the printf function, so that is included in your process. So in terms of the left three term, so the printf call is implemented inside your environment. So it's not the part of the kernel, it's part of the user level process. So you are still in ring 3. But internally, printf, they need to access the console hardware to print out characters. That's not possible in ring 3 because the operating system blocks any kind of access to the hardware directly. And that's the security purpose, and then we will learn more detail about that later. So internally, it will make a function call called the syswrite, but it's not a regular function call. It requires a transition from the ring 3 to ring 0. Then the operating system will catch that and handle the request. Because the operating system has the full access to the hardware, they can talk to console hardware, print the character, and then they need to resume the user program execution of here. And to do that, we use the iret to getting back to ring 3, and then that gets back to the context of the library call of the printf. And then we will use regular function return to return back to the original program. And after knowing that, today we will learn more about the system calls and how can we protect a user level program from accessing any kind of the part of the kernel, but just accessing the system call points, not the arbitrary function. And also we will take a look at the case of handling fault. So I explained that the fault is a part of the exception. So that's definitely the error. But fault is an error that we can recover and continue to execute. And then I will give an example of how we can do that and how we can utilize that for a good purpose of the operating systems as an example, with an example of the page fault. And then in the lecture, we will go over how we can utilize page fault handling to implement the automatic stack allocation, implementing copy and write, and also implementing swap-based virtual memory using the disk drive to store the data overflows the main physical memory. So we have learned the ring 3 and ring 0. And the main purpose of separating ring 3 from ring 0 is for security and protection. So think about the case. So operating system, on top of that, we run multiple applications. But whenever you download the program and run it, do you actually verify the content code of the program? We don't do that. We just trust if that's Google Chrome, then that's from Google and just download it and run it. But there's always a chance that any program can be a malicious program. So the first party of the software vendor, they may plant some of the malicious code in there. For example, many of the companies right now, for example, Apple, Google, Facebook, they are all implementing, it's legally okay, but there's some part of the stealing the users' activity behaviors and then use that for the advertisement or something. Yeah, so that kind of thing is problematic. And then there should be the way to protect the users from like the applications are accessing that kind of information from the operating system side. Yeah. And then another case could be not all applications are perfect. That means some of the applications could have the security vulnerabilities. And then you will be surprised at how many of the security vulnerabilities hits to the Google Chrome web browser. So I believe like in a month, we are seeing more than 10 vulnerabilities from Google Chrome. That means there are more than 10 ways that hackers can hack your computer while you are using Google Chrome every month. Yeah. So that we are living in that kind of insecure world. So that we need to have a layer of the protection. So even if one of the applications are malicious, operating system need to be there to protect the entire system. Yeah. So one of the examples that a malicious program or hacked program could do is that, so now we all know how the computer boots. And then by just changing one bit at the end of the bootloader, that was 55AA as an hex code. If you change any kind of one bit of that 2 bytes, then the BIOS will not regard that as a bootloader, then that will result in like a boot failure. So suppose the malicious program directly access the hard disk and then change the bit. Then after the reboot, your system will never boot again. Yeah. So we need to protect the operating system or entire system from that kind of activity. And then we can definitely do that. And then that's the job of the operating system. And the main reason, so I just give some of the examples of it. So the main reason, the reason why operating system take the part of in the middle of between the hardware and the application is that the operating system wants to monitor all the activities happening in the Ring 3 side, and then only allow the legitimate good things for the system at here. And then after approval, then the user level process can access that. So what that means is that, so if one of the program attempts to overwrite the bootloader, then the operating system need to block it. So the implication is that the operating system must mediate all the hardware access because the hardware access from the user level Ring 3 could be malicious. So the operating system need to monitor that. And if that's definitely malicious, then they need to block it. And then in this kind of structure, we learned about the library calls and system calls. And then the reason why we are learning the distinction between two is like the system call is something like, conceptually something like a function call, but it is implemented in a totally different way. So for the library calls, I explained that that's included into the Ring 3 space. So that's basically within the user processes the virtual memory space. And then Ring 3 application can freely access that, and they can even modify the content of the library calls. So they can even overwrite the printf function and then like change it to do something else. So that's totally possible because that's their own program. Yeah. And then the distinction between the library call and system call is that to access the hardware, we need to invoke the system calls, and then system calls are residing in the operating system. And some of the system calls are exposed as a C library. For example, you can use read, open, write, that kind of function call. And then these are implemented as a library at here, but internally in the library calls, it invokes the system call, a corresponding system call. For example, if you call the read function, then internally, it will invoke sysread system call at the operating system side. So The execution flow is that the app invokes a library call, and then library call invokes the system call, and then operating system checks if the system call is legitimate or not. So think about the example. Suppose that this is a write system call, and then if the application launches the write system call to the boot sector of the disk, then that should be prevented. So the operating system can take a look at that, whether the current system call is legitimate or not. And then if it is not, then they just block it. They just return with the error code and then do nothing. But if that is a legitimate call, for example, just creating a new file and then write into their own directory or something, then that should be allowed. Then the operating system is something like a gatekeeper and then take a look at what's going on and then only allows the things good for the systems. Then we can think that there is a library call, and then inside of the library call, it will call matching system call. So I just simplified the diagram at here. So it seems like the one library call calls the one system call, but it's not true. So the one library call can invoke many system calls, but please focus on that internally we can call the library call, but the library call will make the system call. And then these library calls, you can call the functions at any location of the ring 3, but think about the system call. So the code for the operating systems are in ring 0. That is, so the code area for the memory is marked as PTU as 0. So ring 3 application have no access to the kernel memory. That's what we learned from the page table and then virtual memory. We can do that. And we actually do that. And then even if we don't have access to the operating system code, then there should be a way that we can invoke the function calls to the operating system from the ring 3 library calls. Then let's take a look at the details about how can we achieve the controlled execution at the operating system side. And before getting to there, let's take a look at some of the problems if we do not have like a good mechanism to gatekeeping the system calls. So when the printf calls syswrite internally and scanf calls sysread to read the user input, and send runs a syssend to send the network traffic to the other end, that's okay. But suppose there's a other function. So the other function could be page init, page alloc, or that kind of functions that you have implemented in lab 2, because that is also in the operating systems in memory as a ring 0. So technically, if it is wide open, then if there's a bad function, some of the bad function was implemented in the application side, and then if they can manage to call this kind of other function. For example, if that is pgdir walk and then like page insert, then the user level program can map arbitrary virtual memory to physical memory and then change permissions, and that could happen. So if this kind of the function call is possible, then the ring 3 application can do whatever the operating system can do. So we should prevent that kind of thing. And then we should not allow this kind of thing while allow all these cyan colored arrows. Yeah. So these are the right positions to make the system call. And then this is not the one. So conceptually, what we need to implement is something like this. So operating system should only open the door for system call, not about the calling arbitrary functions. So blocking all this kind of access from the ring 3. Any questions? So the thing is, like, if the application can call arbitrary function, then that's actually the same as like the application became an operating system. So we should block that. And we implement a so-called call gate using the interrupt and trap mechanism in JAWS. And then we use this similar design in the modern operating systems. And then let's take a look at how we implement the call gate. So what we want to do is just linking the printf to syswrite and then like not allowing any kind of function call to the other function. And how do we do that is, so we implement the trap and trap dispatch and that kind of functions. And then at the trap handler, we combine all the interrupt traps, those kind of thing into one single function and then dispatch that again. So the way that we are calling a system call is not a regular function call. If that is true, then we can call any kind of function here. Instead of doing that, so whenever you make a printf call, internally, it wants to make a function call for the syswrite. And to do that, it will generate the software interrupt. Same thing happens for the scanf, send, write, fwrite. Internally, if they have to invoke a system call, they need to generate the software interrupt to switch from ring 3 to ring 0. And then whenever the interrupt happens, it will get into the trap handler. And then in the trap dispatch, we will identify based on the EAX number, if that is like the 0x30, then we know that that's a system call. And then that gets into the syscall function in JAWS. And in that function, based on the system call number, it will dispatch again. So if the number is 1, then it maps to the syswrite. If the number is 2, then that maps to the read. 3, then it maps to the send. And then at the trap, so the trap is somewhere that the ring 3 application tries to invoke the system call. And then we trap that call at this area. And then as the operating system, we monitor if the current call is legitimate or not. So at here, we can actually take a look at the write or that kind of system call. If that goes to the boot sector of the disk, then we can prevent that. So if that is true, then what we can do is we can just return -1 or some of the error code to the user level application. Otherwise, if that write is just a regular file write, then we can pass through and then run the system call and then return back to the application. Any question about this kind of the call gate design? Yes.
So basically, this call gate is just to isolate, so it doesn't call any other under it.
That's right. So like in the diagram, what we want to do is like a mapping ring 3 functions to the ring 0 function, right? Yeah. And then instead of doing that, we would like to build a single point that all sort of that kind of system call gets in. And then at that single point, we can examine the legitimacy of the system call by examining the argument, file descriptor, that kind of information. And then if that is legitimate, then we can pass the request. Otherwise, we reject the request. And also another purpose is that the system call can only happen for this kind of the selected functions, not about the arbitrary functions, because the code that will manage this kind of the system call dispatching will never have path for the calling other functions. Other question? No? There's one question from Zoom side. So the question is that does the ring 0 function get called based on the ring 3 function name? So it's not true. So we have learned about the system call calling convention. So in JAWS, we put the system call number at the EAX register, and EDX stores the first argument, ECX second argument, EBX third argument, that kind of order. So the value in the EAX will determine like which function to call. So for example, if the system call number for syswrite is 1, then printf, before calling the system call, it needs to put the number 1 to EAX and run the software interrupt 0x30. Question?
So when system function returns, the return value will be in a register?
So like in x86 calling convention, we put all the return values in the EAX register. So think about it. If this function returns, so in the EAX register, it will store the return value. So usually the return value of the right system call, if it gets through, then the number of bytes written. For example, if it is 5 bytes, number 5 is stored into the EAX. And then before returning back to the application, so we have the trap frame of the application. And in the trap frame, we store all the registers, right? And then we update ring3 EAX stored into the trap frame to the value that we got from here. Then that value will be delivered at here as the result of the in the EAX register. So the application just read the EAX register, then they can fetch the return value. And then in lab 3, when you are implementing the system call, you need to update the trap frame EAX to deliver the return value back to the user level program. Any other questions for this call gate? So this is a conceptual description, so you will be much more clear when you finish or when you get to the implementation of the system calls in JAWS Lab 3. So we will exactly implementing this kind of call gate in a trap dispatch and syscall function in JAWS. And then to get across this kind of a call gate, because we need the ring switch, because this part is also ring 0. Yeah. So user level application do not have any kind of access to here. So after they fail the register and then invoke software interrupt, then operating system will take care of the rest of the things. So to invoke the system call, we need to fill the EAX as the system call number, and then EDX, CX, BX, those kind of the registers as a argument order, so that you can refer to the slide for the last week's slide for the take a look at the argument order correctly. And then after filling all of that, to execute the call gate, you need to run software interrupt the 0x30. Yeah. So this is just for like the invoking the system call. And then the handler for the 0x30 at the IDT, interrupt descriptor table, will deliver that into the syscall function, and then running the matching system call accordingly. And this design is not particular to JAWS. So in 32-bit Linux, we use software interrupt the 0x80 as a number for the system call. And then in Windows 32-bit, we use software interrupt the 0x2E as the software interrupt to invoke a system call and access to the call gate. And then because when the interrupt happens, it stores a lot of information. Yeah, so that we simplify that, like we only store the trap frame when the interrupt happens, but in the real operating system, we need to store a lot more of the information when the software interrupt happens. Yeah, so the CPU designers, they create a separate instructions just for handling system calls. So it's something like CPU has been designed in 1985, 80386. At that time, operating system was not that developed like that. So we didn't know about like there's a need for the system call, virtual memory, these kind of thing. But later, as the software development enhanced by, then the developers need for like the new instructions or a new way, faster way to access the same thing. So later, I believe the sysenter and sysexit, that is implemented in Pentium 2 CPU in 1997, I believe. Yeah. So they implement the sysenter and sysexit. But conceptually, what it does is like a similar thing to the software interrupt. but they ignore the storing some of the hardware specific values at the CPU side. And that's why it's a little bit faster. So one of the extra credit in Lab 3 is that we are using interrupt to 0x30 for switching from user level to kernel for system call. The extra credit, the challenge for that is in Lab 3 is implementing system call using sysenter and sysexit. And then the similar thing happens when AMD designs their 64-bit CPU in 2003. They implemented the very similar instructions, and then the name is different, syscall and sysrate. So how you can regard this is that using software interrupt is an old way to switch from the user to kernel, but it's general. You can use it for any kind of switch. But later, CPU designers, because the system call design is quite popular, they optimized system call in and out with these kind of instructions, so that these are the new one. And then, because the switching happens with the interrupt or this kind of the ring switch instructions, so whenever we take this path, so execution switches from ring 3 to ring 0. Because regular applications can never access a ring 0 space. We can do whatever monitor, whatever check, and then after checking the legitimacy of the system call arguments, so we can apply the check for that, and then for the legitimate one, and then we can pass it to get through the execution for the system call, for example, accessing the hardware. And for next, let's take a look at some of the real examples that how the operating system is protected by the call gate. So let's take an example of the read system call. So this is the description of the read system call in Linux. So I will give an example with the real operating system. So how we use the read system call is that we need to set the read system call number to EAX. And then as the first argument, we put the file descriptor and then buffer, address, and then size of the count to read count amount of the data to the buffer. So for example, if we set the buffer size as a 512 byte and then run read 0, so the file descriptor 0 means that we are reading from the standard input, which is the console. So it will get the keyboard typing of the users, and then up to 512 bytes. After running this, it will put the data in the buffer. So this one does not have any kind of problem because the buffer is a ring 3 memory, and then user interacts with the console. So type 1111 or something, and then that data will get into the buffer. But let's take a look at one of the problematic case. So suppose, so this code is wrong, but let me describe it correctly. So suppose we have the kernel address. So from kernel base and up in JAWS, so these are all direct mapping of the physical memory, but these are marked with the PTU all 0. So the user level should never access that. But suppose this is a variable buffer. Suppose what will happen if we invoke the read function with the kernel address on it? So suppose this is the address for syswrite or something. And then it will run the read system call. That means let you type some data. And then when you type the data, that data will overwrite the kernel memory. And then if that's set as the syswrite function, then you can overwrite the function. And then later you invoke the write system call, then it will run completely different function. So the overwriting the kernel memory should definitely be prohibited. But the problem is that, so this read function call happens in ring 3. But when it gets into the system call, reruns internally at ring 0. So accessing this kind of the kernel address is totally available. Let me show you this description more correctly. So suppose the application invokes the read function with the buffer here, and then it will get to the system call gate via trap, and then operating system can check the argument. So for the second argument in JAWS, that will be stored into the EDX register, and then try to check that virtual address is marked with the PTEU as 1. So that means the address is accessible by the application. So in that case, if that is the user address, then the operating system let the system call pass through, then make a call. This is how it works. But suppose the application put the kernel address on it. Then it will get into the trap. And then the first thing the operating system will do is like to check if whether the second argument is the PTU is up, user memory, or not. And then operating system figured out that this is a kernel address, and then the application should never put the kernel address for the read system call, then it can return with the error. And this is how we can use the operating system to monitor over the system call gate to protect itself from the malicious use. Then let me show you the real example. So this is the code, and then this is a stack buffer, and read to the ring 3 stack buffer is totally fine. So I just put ASDF ZXCV, and then that will be put onto the buffer. And then because I typed the 8 characters and the enter, so the return value is 9. Because I supplied the 9 characters, and this read function have read 9 characters. So the first call to the read was successfully handled by the operating system because we put the user address. But in case if we put the kernel address, so address starting with the FFFFFFF, this is 64-bit Linux, that's why the address is quite longer. So address starting with the FFFF something, so these are all kernel address. And then I just put the start of the kernel address at here, and then read 512 bytes, and then it returns -1. And then I try to print the reason for the error, and the operating system says that address. So what they did is like they indeed Linux operating system apply the check it here, and then do not allow the putting kernel address for the read function here. And then in JAWS Lab 3, you also need to implement this kind of the checking function to not allow any kind of user program arbitrarily override the kernel memory. And then there are some of the tools that you can easily take a look at how the application uses system call. So on Linux, I believe that you can run it on the OS2 machine and then any other Linux machines. So there's a command called strace. So it's shortened form of the system call trace. And then you can run application by wrapping with it. So what that means is like if you want to run the bin ls application, then if you run the command as a strace and then target program, then it will run the target program and then print out all the system calls and the argument for that. So this is not a strace of the bin ls, but the strace of this application. So what I wrote is read printf something, and then it calls read system call, and then printf is internally switched by the write system call, right? So that you can see all these kind of the system call interactions. And then let's take a look at these 2 read system calls. First one is a 0 buffer, and the second one is a 0 and the kernel address. And then the first one is a 0 and the buffer, and then it has been executed correctly with the return value 9. And then for the second read, 0 with the kernel address, and then that returned with the bad address -1. And not related to the operating systems, but this is the trace of the system call. But if you're curious about like how the applications utilize the library functions, there's another command that you can use called the ltrace. So it's for library trace. And then if you wrap the execution of the application using ltrace, then it will show you how the library call has been made. So you can see that this is more similar to this source code because the read printf Pieter. Read printf Pieter, right? So ltrace, because we are using library calls in writing the applications. Yeah. So the ltrace is more matching to the source code of the program, but internally the libraries will make these kind of the system calls. And then strace shows that the how application interacts with the operating systems. That's the implications of the strace and the system call. So the summary of the system call and call gates. So we need to protect the Ring3 application arbitrarily runs on the operating system. So we should not let the applications run the arbitrary part of the operating systems because we do not trust the user application at all. And then the operating system need to mediate all the hardware access. And to do that, we need to have some sort of the API. And then we only need to make the systems allow the correct API point as an entry, not about the arbitrary function call can be possible in the system. And to enable that, we implemented call gate kind of the design. So all the system call need to gather on the single point. And then in the ring 0, we can apply the check to decide whether to reject or approve the request to the system. Any questions about the call gate? All right, let me move on to the next. So next is about the handling fault. So I explained about the trap, fault, interrupt, exceptions. And then the exceptions are all sort of the errors that the CPU gets while executing the program. And then we will point a fault as an exception that we can recover and resume the execution. So I believe like some of you cannot get like what is the error that we can recover and continue to execute. Yeah. Then so that's the important part of the fault. But let's take a look at some of the cases of the faults that we can utilize that for a good way. And as an example of the page fault. So page fault, the name itself says fault, and then that means we can recover and execute the program again. And then let's take a look at when it happens. But before that, let's learn about like when page fault happens. So the page fault happens whenever the address translation. So reading the page directory, page table entry, and then comparing the permission flags, and then whether to apply write access, read access, kernel access, user access. So if there's any kind of error, then it will generate the page fault. So whenever we translate, we attempt to access a virtual address. If their page directory entry or page table entry misses the PTE P bit as 1. So if these are 0, then it is invalid translation. So CPU will generate the page fault. Or if we apply the write access to the address that has page table entry has PTW as 0, then it will generate the access violation. And then whenever we make an access from user to the virtual address that does not has a PTEU bit as 1. If that's 0, then that will generate the protection violation. Yeah. So the example of the page fault is that, so this is a user program in JAWS, and then we just put the kernel address. So the address starts with the F, and then that will directly access the physical memory 10000 as a direct mapping. And then that page table entries are all marked as a PTU as a 0. So if we attempt to make a write access on that memory, so that should be prohibited. And then this character exclamation mark is the ASCII code 0x21. And then this address plus 100. So the 100 in hexadecimal is 64. And then that's why the target address for the kernel address plus 100 is at the F01000064. So that's the kernel address to store this character. So that's the access the current code is making. And then if we do so, it will definitely generate the page fault. And then if that is not handled in JAWS, then you will see that the stopping of the program by seeing this kind of trap frame. And then this trap frame says like the trap number is a page fault, number 14. And then the error code has a user write protection fault. And then CR2 register F01000064. So the CR2 register exactly stores the faulting address. So the address that is problematic right now. So the trap frame will give the information about the reason about the fault, where it happens, so that kind of the context is stored into the trap frame, and then that will be delivered to the operating system when we handle the page fault. And then let's take a look at more detail about this kind of the error code. So whenever page fault happens, CPU will automatically store the address that is problematic in accessing right now, that to the CR2 register. So it's stored that the problematic kernel address to the CR2 register. So at the page fault handler, we can know that which address was problematic. And then, so the CR2 register will store this value. And then in the error code, so the error code will store this kind of information. But the important thing here is that the last 3 bits, P, W, R, US. So if the P value is 0, that means the fault is caused by there's no translation. That means like a target PTE or PDE, the P bit is a 0. And then if that is 1, then so target is valid. So it's not about the translation error, but it's more about the protection error. So we got the number 7 for error. And then right now, the target address is translation is valid, but the PTEU is not there. So that's the protection fault. That's why we got 1 here. And then, so read write. So the 0 means that the current access was read. 1 means that the current access is write. And then the access that we make was like writing this value to the kernel memory. That's why we have a W flag as 1. And the third last flag was a user supervisor. So if that value is 0, then the access was made in ring 0. If that is 1, then the access is made in by the user. And because this is the user level program, that's why the error code it was generated by the user level program. So the important thing here is that like whenever page fault happens, then we can gather the information about what is the problematic address, and then what was the reason about the page fault in the error code from the trap frame. Then let's take a look at how the operating system gets that information and then handle the page fault at the high level. So everything written in blue runs in ring 3, and then everything written in red runs in ring 0. So from ring 3, the user program accesses the kernel address. And then the CPU will generate the page fault because there's no PTU flag up for that page table entry. Yeah. Then what CPU will do, it will put the faulting address, this address, to the CR2, and then collect the reason for error and then build the error code, and then call the page fault handler written in the IDT, interrupt descriptor table. And then in JAWS Lab 3, you will create the TPGFLT, that function, as a page fault handler in the IDT, but later it will be dispatched to the trap dispatch and then run the page fault handler. So how that execution goes is that, so in the OS, the CPU will call the page fault handler in IDT, that's the TPGFLT, and then that will call all traps, trap dispatch, and in the trap dispatch with the switch case handler, you will call the page fault handler for that. And then inside the page fault handler, what you can do is, because you have the trap frame, you can read the CR2 to reason about which address was problematic. And then you can also read for the error code. The CPU automatically stores the error code, and then you can read that, and then you can reason about why the fault has happened. And then, as an operating system, we can take a look at the fault, then examine the reason, and then if that is a recoverable case, then we can handle the fault and continue the execution. That's why it is called as a page fault, but I have not yet described about what kind of examples are recoverable and we can continue the execution. And then just understanding at the high level. So when the page fault happens, CPU will give the reason and then which address was problematic and then all those kind of information. And then as an operating system, we can get that information. And if we can recover that, we can let the user execution resume, then they will attempt to have the same access. And then if that is handled, then it will continue to execute. But the problematic thing is that the previous example was like a writing on the kernel memory from the user, and that should never allowed. So the right correct behavior for that kind of error, handling that kind of error is like a kill the user process because they have access to the wrong address. But from now on, let me introduce some of the examples that we can utilize page fault handler to implement some of the features of the operating systems. So I believe most of the students here have finished lab 2. And in lab 2, when we build the JAWS memory layout, we allocate the stack. So that part is a kernel stack, but in JAWS Lab 3, we also need to allocate the user stack. And then that will be used by the program whenever they make whenever we execute this kind of program, so that this kind of buffer, 512 bytes, so that kind of buffer need to be stored into this kind of stack. But the interesting thing is that when you finishing lab 3, we only allocate one page to the user program stack. And then one page is 4 kilobyte. So that means you can have a local variable less than 4 kilobyte. That's the restriction. And then there's a no mapping down there. So if we allocate 8 kilobyte, then it will generate page fault. So suppose you allocate the large local variable, for example, allocating the buffer 8 kilobyte, and then try to write number 1 to that address. That will hit this not mapped address. And then it's regarded as a stack overflow, and then it will just generate the page fault. Then let's think about a new idea about the resolving this kind of problem. So we don't know at the start, we don't know how much stack the program will use. So that's why we just allocate one page to not to waste the physical memory at the start. But in some cases, applications wants to use more memory, then can we automatically increase the stack size whenever the program requests? And then can you do that transparently? So the one way is that like if the applications wants to use more memory than 4 kilobyte, they can invoke a system call to allocate new memory. But the thing is, can we do that automatically? Whenever stack overflows, then the operating system catch that and then give more stack memory to the application. So the reason why I'm asking is like, this is a rhetorical question. So that's yes. And then in doing that, we will utilize page fault. And then the observation is that, so take a look at this kind of the fault. So we have the existing stack. And then if we try to allocate the larger memory, bigger memory, the memory buffer than the stack, then it will be somewhere near there. Like this, right next page or a few pages next to the stack. So the observation is that the stack overflow will be sequential. So the fault will happen near the mapped page of the stack. And then the fault can happen either at the read or write access. Yeah. So we need to catch both of the fault. And then for the next, I will describe like how we can automatically increase the stack size using the page fault handler. So suppose we have a dysfunction in the user level. So it allocates the 32 bytes of the buffer and then try to write this kind of value there. And then suppose the current stack is composed like this. So we only have one page for the user stack. And then stack ends at this address. So there's no map to space down there. And then suppose the current value of the ESP, so the real end of the stack is at EEBFD1010. That's exactly this address. So little above the 16 bytes above the end of the stack. So here. Yeah. And then whenever we allocate the new buffer like this, so we subtract the 32 bytes from the ESP and allocate that. So the buffer is actually at here. So the buffer points to the memory that is not mapped at all. Yeah. So the buffer is right here. And then, so the buffer range is this one. So the letter 16 bytes are okay to writing in this area, but the first 16 bytes, there's no backing physical memory at all. So when we access buffer 0 to put character 1, then so the instruction for this one is like the putting 31 is this one character number 1, and then put that into the memory pointed by the buffer, and then because there's no mapping, no translation, yeah, so it will generate page fault. Yeah. Then at the time of the page fault, we know that the which address is the problem, and then we know that if that is a user access, write access, and then if that is caused by no translation or not. So the rule is, if the faulting is happening near the stack mapping, and also if that is coming from the user, then can he automatically allocate the new stack? Because that's the case where the user application need more stack to store the thing. Then can he do that automatically? Definitely, yeah. So the reason for having the page fault was like there's no translation because there's no mapping. And then the CPU will store the problematic address to the CR2, and then it will set the error code, and then it will raise the interrupt 14. Because we attempted access to the not mapped area. So that interrupt, the page fault error, page fault, that will make our page fault handler invoked in the trap dispatch. And then at there, we can read the CR2 register. And then we can also get where the current stack end is from the environment structure. And then we can identify the problematic address is near the stack end. And then we can also read the error code that. So the fault caused by the translating error. There's no backing physical page. Then the operating system can reason about, oh, the application wants to have a more stack, then we can allocate that for the application. So how can we continue to execute is that? So internally, we can get a new page. So that I'm using the same term and just left 2. You can get a page log, get a new page for the stack, and then run page insert at this page, and then put that in. And after that, iret. So we are continuing the user execution. Then previously, this access was generating the fault. But when we return to the application with iret, for the fault, it will resume the same instruction. But for now, we have the stack backed by the operating system. So now the translation is valid. This is a valid address. Then the program can continue to run. So the implication is that, so by exploiting the page fault error and the page fault handler, if we set up the rule correctly, then we can, as an operating system, we can transparently identify whenever the user application needs more stack, and then we can give them more memory and then continue to execute the program. Any questions about the using page fault handler for automatically increasing the stack like this? Yes?
Actually, what is the physical memory itself already?
So if the physical memory is full, then the page alloc will return 0, right? So in that case, we need to kill the process, no more out of memory. Yeah. But otherwise, we can allocate the new stack and then like let the application continue to execute. Then let me continue to like give an example of like how we utilize this kind of the page fault in the real operating systems. So the previous example, we do not use that, but I just want to showcase like that we can utilize page fault in that kind of purpose because that example is easy. So the 2 other things that we are actually using in the modern operating systems as a mechanism is called a copy on write and the memory swapping. And then both of the things are like restricting the limitation of the virtual memory. So one of the things is like the copy on write is technique to reduce the memory footprint. So and then it lets the sharing memory pages as a read only. And then whenever there's a write, then we give the private copy to the specific process. And that's how we reduce the memory footprint. And then we will see the details about that in a few slides. And then the memory swapping is 4. So in JAWS, now we only have a 128 megabyte of the physical memory. And suppose you want to load 1 gigabyte of the program. Then in the virtual memory, there's no restrictions about like a virtually allocated one should be allocated in physical. So we can put the memory pages in the physical memory. And then we can conceptually also can store those memory pages in the disk. And then whenever the application read, then we can load it later. So we can combine the physical memory and then hard drive as a one big chunk of a memory. and then we can give that kind of the virtual view to the operating system in the application. So suppose you only have like 16 GB of memory, but you have a 1 TB of the SSD, then you can technically running the 1 TB plus 16 GB of the data programs. Yeah, and then that's available in the modern operating system. And then let's take a look at the how we can implement those kind of things. So first one is the copy and write. So the copy and write, so as the name itself says, we do copy whenever write happens. And then this mechanism is for reducing memory usage on the server. And then let's take an example of our OS2 server. So PS lists like all the processes running on the server. And then I just want to check like how many of the bash, which is a shell, the command line processor instance are running on OS2 server. So that program is used by like the 826 times. So currently running on the server. And then Tmux, we use that for splitting the window, and then that is staying there for a while. And then that program runs 128 instances on the server. And then many other applications are running like that. Then think about it. So we have 826 instances of the bash program is running. Then does that mean that do we need to have the copy of the bash program 826 times? So in the lecture, I explained about like although we are using Google Chrome and then opening the 80, 90 tabs, we do not have the Google Chrome binary for the 80, 90 times because we share that. And then this is the mechanism that how we can share the memory and then reduce the memory footprint. Yeah. So the important concept is that we are running the same program. Then let's share the same part across all the processes, but just specialize the change it part. And then before explaining about the copy and write, let me describe a little bit about the program address space. So we learned about the ELF header. So that's a Unix system uses for the executable binary. And then in the ELF program, we have several sections. So the text section is for code. So code area, generally readable, but not writable, but it should be executable because that's the code. And then there's a data area called RO data, read-only data. So that's the read-only, not writable, not executable. And then general data area, it has like the readable, writable access. But the data area means that some of the global variables that has been initialized in the code. So that falls into the data area. And then another area called BSS. And then I don't know why the name of the thing is called as a BSS, but you can regard that as an uninitialized global variable. But the important thing here is that in the program, there are some part of the read-only, but there are some part of the writable area. And then we can easily think of, for the read-only area, we can freely share that to across all of the processes because the content of it will be never changing. But these kind of the BSS and data area, yeah. So suppose you are running same program for 100 times, but the reason why we want to run the same program for multiple times is that we want to process different data. So for example, one of the bash instances for me, and the other bash instance is for like you or some other students, and then we are playing with the different data. So that kind of the differences will be stored into the writable area. Then how can we share this kind of the writable area also? That's the challenge here. So if you just share the read-only part, then there's no problem. But the reason why we are using copy and write is like we even want to share the writable area too. And then let's take a look at how we can do that. So suppose the program is something like this. And then you can regard this as a physical memory. And then whenever you run the same program as a new process, then you need to copy the entire thing as a physical memory and then build a virtual memory for that and then run the instance. And then whenever you invoke another program, then we need to copy all the memory and then build the physical memory and virtual memory and then run the process. So the question is like, do we need to copy all the same data again and again whenever we create a new process? So the answer is no. Then how we can do that is like that we can share all the page by regarding them as a read-only. And then we will handle the writable thing later. So the thing is, suppose we have a one copy of these kind of the area in the kernel, physical memory. And then whenever we run the one program. So the reason why I emptied color for these blocks are, so we are technically creating the virtual memory space for process one, but we will map the virtual memory to follow the physical memory of the single copy in the kernel. But so we are not actually copying this data to back this memory. So it will refer to the same location that is in the physical memory. And then whenever we run a second program, it will refer to the same location. So previously, whenever we create a process, we copy all the thing. But in this case, we don't copy. Just create a page directory and page table to map the virtual address to the same physical address. But the important thing is that regardless of the writable status, we mark all the pages as read-only. And then the reason for doing that is like if we want to catch whenever process one writes on this data, then we want to have a private copy for that. So what that means is that, so let's take a look at the process one only. So that we do not have a private copy of any kind of the program here. And then just a page table maps back to the shared program. And then suppose the program apply the write on the global variable area, VSS. Then it will definitely generate the page fault because this is now marked as a read-only. Then in the CR2 register, we can get the address. And then from the address, we can actually know that, oh, this is the shared one. Originally, it is writable, but right now it is marked as readable to implement the copy and write. Then we can also get the error code, whether the fault is happened by writable, and also it should be valid address, and then it should be coming from the user, and then we need to check that. And if the conditions are matched, what we will do is we will create the writable and private copy of that data just for that process. So what that means is that there is a write, there is a page fault, and then we know that that's happening in this area, and then that was originally writable area. Then we copy it, cut the mapping here, and then map it to the private copy. Then the changes are only available to process one because the other process will refer to this one. So if there's a no write, the single copy will be shared. But whenever there's a write on the shared copy, then we can copy that, create a new mapping, and continue to execute. Then the process one will regard that as like that they have the private copy. So virtually, even if we shared all the program code and data at the start, the program will believe that they do have a private copy. So under the hood, the operating system can catch the page fault and then handle that. And then if we resume the execution, then they can write on the global variable because now they do have the private copy. Then you might have a question about like so Writing it here, we can know that this is readable, writable, so we can process it. Writing it here, it is readable, but it is really readable. Then the write access on default should be access violation. Then we need to kill the process. We should not allow the write access here and then do the copy and write. Then how can we distinguish? So in the page table, we all have the readable. There's no PTEW at all. Then how can we know that the original page was writable or not? So in doing this, we are actually using this special flag called the PTE, copy and write. And then this is defined by the JAWS. And then Linux or all the other operating system, they define it because in the page directory entry and page table entry, there are the area that we can use the bit flags for the available for system use. So these are the reserved space. CPU will never use, but we can actually store the data to mark some of the status of that. And the PTE copy and write, the value is 800. And then if we write down in the binary data, then it's only one placed in the 11th bit. So that we are using actually this bit, the AVL bit, one of the AVL bit as a copy and write. So how will we use that is that, so please ignore this part right now. So when we create this kind of the, not the entire copy, shallow copy of the process space, then if the original memory is writable, then we mark PTE copy and write as 1. Then whenever there's a writable fault, then we need to copy and then map the new physical memory. But for the real read-only data, we mark the PTE copy and write as 0. And if the fault happens, writable fault happens in this address, then we can regard that as a real fault. Read-only, apply the write access, we need to kill the process. Any questions about the using PTE copy and write for that? So thanks to the early stage system designers, even if they don't know, we can utilize the page fault as like this kind of the mechanism. They reserved bits at there. So that's why we can implement this kind of feature. So the benefits of the using copy and write is that like we can reduce the time for copying contents whenever we create a new process. So whenever you create a new tab on Google Chrome, what it does is like it will minimally generate the page directory and page table and then run it. And then whenever it writes on some of the memory, then it will allocate the new memory for the new instance. And by doing so, the CPU and the operating system will map the memory very lazily. So that it will map the physical memory only if it is indeed required, so that it can reduce the memory footprint for the writable area if the data has not written yet. Yeah. So the implication is that by exploiting the page fault and the handler, we can implement the mechanism called the copy and write, and then we can reduce the physical memory usage and then share the pages. Now it's getting over the time, but let me have 3 minutes to explain the last thing. So last thing is about the storing the memory pages in the disk. And then the reason why we need to utilize the disk is that, so faster memory is expensive. So registers are the fastest memory, but we have a limited number of registers in the CPU. It's only 8 kilobyte or something. And then we have cache. That's the fast memory in the CPU, but we only have 30 something megabyte of the cache. But for the main memory, we have several gigabyte. But our data is so enormous, and then it doesn't fit the several gigabyte, and then sometimes it requires a terabyte, petabyte, and then need to go to the disk. Then most of our systems are limited by the size of the main memory. Yeah. Then we have the disk, and then the simple idea is that can you utilize the disk as a memory? And then we can actually do that with the page fault handler. And then how we can do that is something like this. So suppose we have 2 pages mapped in the virtual memory, green one and the yellow one. And then with the page directory, it will map to this one, and then that will map to that one. And then suppose we want to move one of the physical page to the disk to free the physical memory space. And how can you do that is that, so there is a disk, and then, so we want to remove this green mapping. Then we can remove from the page table entry, and then remove the physical memory and store into the disk. Then, whenever there's an access, there's no entry, it will generate page fault. Then what we can do is, whenever page fault happens, we know the faulting address in CR2, then we can consult the disk if that address is stored in there. If it is, then we can map it back and continue. So the logic is, so that at the page fault handler, we could get the faulting address. And then if the error code says the caused by translation error, the page is not presenting, then the faulting page may be stored into the disk. Then we can look up the disk if that address of that process is swapped out to the disk. And if it is, then we can load that to the memory. And then continue to execute. That's why it's called a fault. We can continue to execute that. So the final diagram about the swapping is that whenever this access happens, and then we got the page fault, then we can consult to the disk. And then if the target page found, then we can map it back like this. Then continue the execution. Then the application will transparently fill that, because the application don't know what's happening in the operating system, and then it will just return. But in their viewpoint, the virtual address is the same. They don't know about the internals of the page directory table and physical memory. So what they will see is seamlessly loading the page from the disk, and then they even don't know about whether that page is like swapped out to the disk or not. So the summary of the lecture for today. So for the last part, we learned about the page fault, and then it will be generating whenever there is a translating error, access violation error, or protection error, readable, writable, user kernel, or presenting, not presenting. But because the CPU will collect the information about the faulting address, reason for the error, we can reason about what was the fault, and then we can utilize that page fault handler to implement some other mechanism. The example was like the automatic stack allocation and copy and write and swapping. All right, thank you for your attention for 10 more minutes for the last part of the lecture. And then like this is the end of the today. And then feel free to come down to ask questions. One question from the Zoom side is swapping more things more slower? Definitely, because the disk access is much more slower than the memory access. So it would make the entire system a little bit slower. And then like whenever a user program accesses the thing, the execution, the same CPU need to run on the side for the operating system side to handle all these kind of disk access and all the things. Then the page fault itself will take a long time. So the swapping to the disk makes the system much more slower, but that's the way that we can enable running of the larger application than the physical memory running on the system possibly.